Hmm. Okay, so we are continuing from this transition system. We said, okay, transition systems are a way to reason about complex program behaviors. Um, so here is a nice example. So earlier we had looked at factorial, and we had a lot of work done for factorial just to show that the factorial was right. Now what we're doing is we are actually doing something um, much more useful, right? Than say you would admit a factorial list. Um, I don't know why it's sort of okay. So Google Meet is sort of misbehaving. Okay, anyway, I have to admit session price now. But anyway, so what we are going to do is to reason about a concurrent program, right? A shared memory concurrent program, and the program itself is going to do something small. I mean, it's a the thing with concurrent programs, right? If you have n instructions, then there are exponential number of interleavings that are possible, right? 2 power n executions, interleavings that are actually possible. Because the observation is that when you have two things that can run concurrently, you can either choose to run the first thread one step or the second thread one step, which means that you have 2 power n interleaving. So reasoning about concurrent programs, right, is quite a challenge, and it's still an open challenge. Um, there have been lots of excellent work that have been done in the last, say, 10 years in programming languages area in order to simplify concurrent programming. I mean, the significant visible examples are, say, Rust, right? Rust is this language explicitly designed to compete with, say, C and C++ in terms of performance, but arguably much more safe. And Rust, for example, has this a very expressive type system called ownership type system, which tracks how many references, right? I mean, just to talk about it in a very high level manner, it has this notion of resources. Essentially, if I have, say, a system's resource such as memory, right? Rust type checker will actually track whether one person or more than one person has access to this resource, right? And what kind of access that is, whether whether it is a read-only access or a read-write access. This is very nice because once you can actually track statically that two people have access to something, you can sort of say, I won't allow modifications to this memory because some other person also has access to this. If you modify this, then they may see different results based on the order in which the write happens, whether the read happens first or the read happens after the write, right? So this is also useful for memory management because if you know that there is exactly one reference to a particular object, and this particular reference and the program, the function that you are having this reference to, sort of terminates without sharing this reference anywhere else, then you know that you can free that reference at that point, right? So Rust sort of solves two very complicated problems at the same time. It solves the memory management problem that C has, right, without using a garbage collector. It also, thanks to this ownership system, gives you by default a data race free program by construction. So you don't have to deal with any of the data races, right? So this is significant improvement in the last 2 years, and this is thanks to, I should say, 40 years of research on these ownership types and so on. And Rust sort of implemented that. I mean, based on all of those results, but it's an excellent language, right? And I mean, this is a new language, but we also have expressive static analysis that have been implemented in this Infer tool from Facebook. This is an open source tool which you can run on, say, your Java programs. The initial idea was to detect null pointer exceptions, but it can now detect concurrency bugs as well. So if you have something that is accessed by two different threads and you have a data race, where there can be concurrent access to a particular resource, right? There is a particular piece of memory, and one of those is a write. Then we call it a data race, right? So all of this can Infer tries its best to detect all of the data races as much as possible. So these are like two conflicting approaches, right? So not conflict, two orthogonal approaches. One is like the language doesn't provide static guarantees, but there is a tool, static analysis tool, which sort of does the hard work. And Infer is actually built with a lot of advanced PL research, right? Some of which we will cover, hopefully cover in this course this time. Separation logic, concurrent separation logic, and so on. And on the other hand, Rust has an alternative way of achieving the same thing using type system. Both are okay, right? It's not that one is always better than the other one. Again, programming languages are like tools, right? You wouldn't use a hammer if you need to tighten a screw. So that aside, right? Reasoning about concurrent programs is like open challenge, and what we are going to see here is our baby steps into reasoning about a very simple concurrent program using the transition system mechanisms that we built, right? So the program here is very simple. It has 4 instructions precisely, and we are going to reason about 2 threads executing these 4 instructions, right? Intuitively, lock and unlock are what you would understand from your operating system course, right, or concurrent programming course. So if you get a lock, then you have exclusive access to, you are starting a critical section. So when you are within this critical section, you are the only thread which is running here, right? If the global value is initially 0, then the first thread runs. This will be, global value will be updated to 1. And when the second thread runs, it will be updated to 2. And all we want to show is that at the end of this execution, the global value is 2, right? But of course, so these are semantics that we prescribe, right? That when you are in a critical section, other thread cannot be in there and so on. So all of this has to be taught to Coq explicitly, and that is what we are going to do by modeling all of this using a transition system, right? So how do we model this as a transition system? So we have to use the facilities that we know that we have in Coq. So the first thing that we do is we sort of inductively define, we define this inductive data type, which simply encodes the program counter, right? You can sort of say, I am just before executing lock, or just before executing a read, or just before executing a write, where it is parameterized with the local value that has been read in the previous step. So when you see a write for a thread, the thread is just before executing this write to this global variable, where the local variable value is the parameter that is associated with this write, right? Or you're just before unlock, or you've finished the program, in which case you're done. So this is sort of capturing the local state at a particular thread, right? It's fully capturing the local state because we don't have anything else in this simple program. Then we have this global state, right? In order to track what is the lock state, whether the lock is currently held or not, right? And what is the global value at any point in time. So we have the inc state, which is the state that has been shared between 2 threads. So it has the lock and the global variable, right? That's the entire state that we have. And we can sort of write the state from a particular thread's perspective using this record type. So this is a generic record type that is parameterized with some shared state and some private state. So it has 2 fields, right? Shared and private. And the types of those fields are shared and private, right? This is just the generic description. And for our program, which is this increment program, the increment state is going to be threaded state of increment state, which is the shared state, right? And increment program, which is capturing the program counter, but also this local variable that has been read. Okay? So that's the increment state. So this captures the state for a particular thread, right? That the state for a particular thread is composed of the global state that you can access and the current local state, which is the program counter, and the local variable that is embedded in this particular position. So, okay, so this is the state. Now we will define a state transition system. And what do we need to define? We need to define the initial state, the step function, right? So we define the initial state as an inductive type, as we've done before. So how do we define the initial state? The initial state, the lock is not currently locked, right? The mutex is currently unlocked, and the global state is 0. This O is 0. Just read it as 0. And the private state, the thread local state, is locked. The way to read this is the thread is just before executing this lock. It is at the start position, right? So that's the initial state. That's the initial state of one thread, right? And we define the step function that sort of shows how to progress through the sequence of instructions. And we define it as a state-to-state relation, right? So sort of relates two states. And essentially, this is sort of defining the conditions for the arrow. So from lock, right? If the current state is locked as false and the global state is G, the private state is lock, which means you're just before executing the lock. Then you can execute that instruction to go to a state where the lock is now held, right? The global state is still G, and you are just before executing this read instruction. So that's one step. And similarly for the other steps as well. So what comes after read? So you're going to perform the read and move to the write state, right? So you move from read to write, but what are the conditions there? Whatever the lock is L, right? This L is universally quantified here, and G is also universally quantified. The lock state is still the same. The global state G remains the same because you're just doing a read. If you do a read, the value that you have in the next, the private state that you have in the next step is write G, because you're reading this G, right? And that's the G that you are going to associate with this write. So this is essentially capturing what is happening here, right? You're going to do the write, but the value that you're going to write is the value that was read from this previous instruction. So that's the association here. Stop me if you have questions, right? So I'm just going to keep going on, but stop me if you have questions. And from write, we are, what is the semantics of actually doing a write? So the lock is still universally quantified L. The global state is G, right? And we are going to write the value V, right? And if you sort of look at how the write works, it always writes 1 plus the local state that we just read, right? So it doesn't matter what the global state was before, but the value that you're going to write is 1 plus this V, right? The global state becomes 1 plus V plus 1. The lock is still the same, lock is still held, and you're just before executing this unlock instruction. And for the last step, the lock is in whatever state, the global state is G. If you execute this unlock instruction, you basically unlock the lock, right? The global state is not changed, and you're done. So that's the last state. And we don't have transitions from the last state. We don't explicitly define it, but we'll come back to this, right? We don't. We will use the fact that it is done as the final state, but we don't explicitly define it. So these define how you can take steps through the program. Okay, and then using the initial state and the step function, you can define a transition system. The increment sys is the transition system that captures what happens at a single thread, right? So this is just single thread transition system. But now what we actually want to do is to, I mean, this is uninteresting, right? If you just run it as on a single thread, all of this lock unlock business is not necessary at all. But what we really want is to sort of reason about what happens when you execute the program with multiple threads. So here we are going to parameterize this with 2 threads now, right? So so you have what is now. So what are we going to do, right? Let's agree on that first. So we are going to define a new transition system that uses the just defined transition system, right, as a parameter. So essentially, we are going to define how, given that we know how the transition system for one thread works, we are just going to define two threads. I mean, intuitively, what you are going to say is, now that you know how one step can make a step, the parallel transition system includes two states, and you can take a step on either of these by taking a step on one of these threads, right? That's all we are going to say. It looks big, but um, I'll just walk you through it, right? So it's not the intuitive definition is what is going on. So we are defining a parallel system, right? So we call it parallel init, the initial state of the parallel system. It has a shared state, two private states. This is generic, just so that you can see the structure of this, right? So there are two initial states for the threads, init1 and init2, right? And what you end up having is a threaded state where the shared state is this. The private state is a tuple with the two private states of the two threads, right? That is what we are going to end up with as the thread state, right? And all it says is the parallel init is the initial state with init1, init2, and the shared state is sh, pr1, pr2. It's just a pair of the private states. If it is the case that you can show that SHPR1 is the initial state for the first thread, right? Init1 is the initial state for the first thread, and init2 is the initial state for the second thread with SH and PR2. There is a lot of text, but all we are saying is the initial state of the parallel system is composed of the initial states of individual threads, right? So, and that's the initial state. And again, the parallel step is what we define intuitively, right? So I have two threads now. How do I take a step in this parallel system which has two threads? You can take a step either on the first thread or on the second thread, right? And how is this step defined? This is defined thanks to the transition system that is defined on a single thread, right? And this is what we are defining here. So this parallel step function is parameterized with the step function for the two threads, right? And what does it say? This is the step function for the first thread, right? So it's threaded state shared private one to threaded state shared private one. It's relating how the first thread can take a step. Similarly, for the threaded state shared private two for the second thread. And what it's going to define is how do you take a step in this combined system, right? So the crux of the thing is there are two ways to take a step. You can either take the first step, you can either get the first thread to take a step, or you can get the second thread to take a step, right? Let's just look at what the first P step one is, right? So we define a parallel step, step one, step two. The shared state is SH, the private state is PR1, PR2. It can go to SH prime, which is this new shared state, PR1 prime, PR2, right? If you can take a step in the first thread, going from SH PR1 to SH prime PR1 prime. So the first thread is moving the state from SH PR1 to SH prime PR prime. If you can do that, then the whole system goes from SH, the pair of PR1 PR2 to SH prime, the pair of PR1 prime PR2. So and this is the parallel system taking a step on the first thread. We have the exact same thing on the second one, right? So if you can go from SH PR2 using the step 2 function to SH prime PR2 prime, then this whole system, which is composed of SH pair of PR1 PR2, can go to SH prime PR1 PR2 prime. So observe that PR1 remains the same, only the PR2 changes. Okay, so that's how you define the execution of the parallel system, where you can take either a step on the first thread or the second step, second thread. And we have this helpful definition for the parallel system, right? These are type arguments, shared private 1, private 2 are type arguments. It basically says, given one system, which is a single threads system, and given the second system, which is the other threads transition system, you can use those to construct the transition system for the parallel state, right? How do you do that? You just call these functions as the initial step, right? Parallel init takes the initial state of the system 1, initial state of system 2, right? That is what they are parallelized on, right? And similarly, parallel step has these type arguments, right? These are implicitly applied, and then you provide the step function for the two system. So this is record access. I mean, the syntax is weird, but essentially, in order to access record fields in Coq, right, you have to use this the record name dot open bracket the field name close bracket. This is just the syntax. It's ugly, but this is how it works, right? All we are doing is we are just accessing the record fields here. Similarly, we are accessing the um, second system's step function and passing that as the second argument to parallel step. Right. So that defines the parallel transition system with the initial state and with the step function. So if you sort of check what the parallel transition system is, I mean, it is defined on a few types, right? But it takes two transition systems, right, and gives you a transition system where the shared state remains the same. The private state is a pair of the private states of the two individual transition systems. That is all it's saying. Okay, so now we can concretize, right? We've sort of applied everything in a very generic manner. So how do you construct the transition system using what we've defined here, right? We defined an increment system here, right, which captures the semantics of stepping through this program that we have here. So all you do is you build a parallel system using the two copies of the same systems, right? Because we assume that two threads are running the same program, and we are going to ask what is the final state. So we just use the same transition system, two copies of the same, and that defines the increment 2 system. So just look at the name. This is increment system. When you see increment system, it's the system for the single thread. And then we have the increment 2 system, which is the system that is composed of two different threads, right? So what do we want to prove? We want to prove that the intuitive condition, right? Let's prove that the counter is always 2 when the composed program terminates. So there are a few things that are going on here. There is a notion of a composed program, which is thanks to the system that we've just built. The counter is always 2. When we say counter is always 2, the global value is always 2. When the program terminates, the termination condition is expressed by when both of the threads are in state done. Right? And how are we going to prove it? We are going to prove it by introducing an inductive invariant. Right? We are going to introduce an invariant which we will establish as an invariant that holds on the transition system, this increment 2 system, right? And this invariant is inductive, which means that it holds at the beginning of the program, right? Actually, it holds on all of the reachable states of this program. And this invariant is strong enough to show what condition we actually want to show. The invariant is strong enough to show that when the program terminates, which is in the state where it is done, the counter value is 2. Right? So you have to think about invariants which are inductive in order to apply, in order to prove programs which have this nature, where you start from something and then you sort of terminate, and you are reasoning about terminating. You're reasoning about the value state of the program at the final state, right? So we are going to come up with a general invariant, but we are going to make it strong enough such that we can that implies the stronger invariant implies what we want to do. Intuitively, we want to show that the counter is 2 when the program terminates. Okay, so there are a bunch of ideas, right? So we'll look at what they are. Essentially, you want to find a property that holds true for all of the states, right? All of the reachable states. So in order to do that, we define this first idea, which is a function that given a program counter, right? finds out what is the contribution from that thread for the global state, right? So this function is called contribution from. So if the program is either in unlock or done, right? So let's just remind ourselves what the definition is. If the program counter is either just before unlock or done, then you've already done the write, right? And the write would have incremented the counter by 1. So that's why we say that the contribution from this thread with this program counter will be 1 in these two states. In all other states, the contribution of this thread to the global counter is 0. Right? So this is an intuitive definition. The second idea is we have this notion of hash lock. So even though we allow the program to take the parallel system to take a step in either of the cases, if you've actually held a lock in one of the threads, right, the other system cannot make progress until you release the lock. So we have to define this notion of how a lock operates, right? Coq doesn't know what lock means. So we have to tell Coq what does it mean to have a lock and make progress. So here is how we define it. First, we define what does it mean to hold a lock. When do you actually hold a lock? So you hold a lock when you are within the critical section, and the critical section is the instructions here. Oops, these instructions, right? When you are just before read or just before write or just before unlock, you hold the lock. You don't hold the lock when you are just before lock or just before done or just after done. You don't make a transition from done, so it doesn't matter. So the lock is held when you are in this 3 instructions, right? So lock is said to be held when you are in these 3 states. In the other 2 states, it is false. Okay, that's also defined. So the idea here is that given these 2 definitions, right, you can actually compute the global state of the program from the local state, right? So we call this definition stat from private. So given PR1 and PR2, which are essentially the program counters of the 2 threads, the global state locked is true if either the thread 1 has the lock or PR is process 2 has the lock, right? The global value is equal to the contribution from the process 1 plus the contribution from the process 2. So using these 2 definitions, we can actually go from the program counters of the individual threads to the global state, right? The global state involves locked and global. Okay, so that's how we define shared from private. And I define what a lock is. What does it mean to hold a lock, right? Actually, what critical section is, which parts of the program are critical section. But we haven't actually said anything about what the meaning of holding a lock is, which is that if you look at this program, right, it cannot be the case that multiple threads are within the critical section. It cannot be the case that 2 threads are at the read and read, and similarly read and write, and similarly it cannot be the case that one thread is at read, but the other thread is just before unlock, which means that the critical section property is not preserved. So we have to sort of define what it means to hold a lock, right? So we do that. We formalize that compatibility by using this instruction OK, right? So we say we take 2 parameters, both of which are program counters, and we say which of these states are compatible, right? We sort of formalize the definition of when it is compatible. So self is you can sort of imagine the current thread. The other thread is what the program counter of the other thread is. If I am at just before executing the lock, then the other thread can do anything. I haven't got the lock, so the other thread can do anything. If I hold the lock, if I am at read, then it must be the case that the other thread does not hold the lock, right? As lock of other is false, right? If I am at write, then it must be the case that hash lock of other is false, right? The other thread does not hold the lock. And if I have read the value n from the global value, then n is exactly equal to the contribution from the other. It is either the case that it has um, returned the value. In this case, it is very simple, right? We start with the global value of 0, so it is fine. So we say that either the first thread has already completed, in which case I should see 1, or if it hasn't completed, I should see 0. So that is why I relate the states also here. I say that the value that I actually saw from reading the global variable is equal to the contribution from that thread. If the thread hasn't executed, it will be 0. If the thread has executed, then it will be 1. Then I'm just before unlock, right? So which means that the other thread cannot be in the critical section. If I am done, then of course the other thread could be in any state. So that is true. So that is the instruction OK, the compatibility function. So now we have the ingredients for describing the invariant, the inductive invariant, right? The invariant is going to say, um, we define an inductive invariant increment 2 invariant, right? Which is sort of applied, which is sort of defines a subset of these states, right? Shared state and private state. So for all private states PR1 PR2, it must be the case that the two instructions are compatible in both ways, right? So instruction OK is the compatibility function that we defined here. So instruction OK PR1 PR2 should be true, and also PR2 PR1, because we have to make sure that the other way is also compatible, right? If both are compatible, then it means that the critical section property is preserved. Then we know that the shared state is can be got from applying the shared from private function. That given the program counters of the two processes, we can build the shared state, and the private state is just a pair of these private states, right? This is what the structure of this parallel system is. So that's why we do this, right? So that's done. So this is the invariant that we have. So our hope is that we can first establish that this particular invariant is in fact an invariant for the transition system, right? And secondly, we will use this invariant to show that the property that we want to do, which is at the end of the execution, the contribution, um, the state of the counter is 2, right? So that's what we're going to do. We are just defining the invariant here. So one thing that we will do as a helper convenience mechanism is that as we will apply this in proofs, right? This term, which is here, the shared from private PR1, PR2, will not unify as it is. So all we are going to do is to lift this shared from private PR1, PR2 to a separate precondition, right? So we are saying, let's call shared from PR1, PR2 equals SH, and all I'm doing is I'm just replacing this definition with SH here. Otherwise, the definition is just the same. It's just, as you will see, it is just convenient to do this here because this is going to be introduced as an existential variable, and it is more convenient to define it as an equality-based definition. So the proof itself is simple, right? We know this fact. This is a fact, right? This fact holds, and this is just replacing one term with another equality. So it should directly work. Yeah, actually, I'm not going to go through the proof in detail. It's so simple that you should do it on your own, right? So, but we've just defined the invariant. We have to establish that this invariant, this increment 2 invariant that we've just defined here, is actually an invariant for the transition system, right? We should show that, and that is what we are going to do now. So it is useful to actually go through this particular step in detail, because the the assignment that I'm going to release after this lecture is done is going to ask you to do the same for a different parallel program. Okay, so that's why I want to show you how to do this. So how do we show that a particular invariant is an invariant for a system? We can show that by applying induction, right? This is what we studied earlier. Is it? Yeah, here. So how do you establish that an invariant holds for a transition system? We use invariant induction, right? How to, and then there is also this how to use them to prove a transition system. We will see use invariant, right? So we are going to apply invariant induction, and invariant induction is going to ask us to show that the invariant holds on the initial state, invariant holds on a step, assuming that the invariant holds on the previous step, right? So that is what we are going to do. So we are applying invariant induction. This definition is previously defined. I'm just using that here. You can refer to it um, in your own time. So we apply and simplify. We get two steps. First is the step for the base case, and second is the step for the inductive case, right? So we are going to generously use invert tactic here in the rest of the proofs. As we saw earlier, invert sort of brings out obvious facts, right? We the invert is first going to be applied on H, right? It says parallel init increment init increment init S and parallel init, right? So if you sort of look at parallel init, um, yeah, here it has exactly one constructor, right? So that's going to make this fact obvious. It knows what the structure of this is going to be, and we are going to keep inverting so that obvious facts just fall through from the definition, from the hypothesis, right? So that is what we are going to do, keep going to do, right? The first time you invert it, we see that what we've gotten is that we know what the shape of this is, and we know what increment in it, the initial state of the individual threads transition system is going to be. So all of that fact is going to become obvious, right? So it says increment in it on the shared state. Again, there is a single constructor here in each of these. So we are going to invert it to bring out that structure as well. So once you do that, right, it becomes obvious, right? So this is, so we know that in the initial state of each of the threads, they are going to be in lock, right? And both of these are going to be going to say that the shared state is false and the global state is 0, which is what we want. And we are going to show that this increment to invariant, right, holds on this state, right? So I'm going to use that by showing this particular property, right? So this is the invariant. This is the invariant actually. So I'm going to apply increment to invariant prime, which is this lemma that I defined, in order to show that this increment to invariant holds on this state. So what does that mean? I have to show these preconditions hold, right? So let's do that. So let's do that. So I have now three preconditions, right? And shared from private is the definition. So let's unfold that. Let's simplify it. And now we have to just show equality. So that goes through. And I have to show that instruction OK lock is compatible, right? So if both of the threads are just before entering the critical section, that's fine. Right? So simplify. Propositional, I don't know whether we saw this tactic. So propositional is a tactic that sort of discharges propositional logic rules. All of your assignments from the logic lecture, right? Most of it can just go through with propositional. It can also go through with auto, but propositional is powerful enough to make all of that go through, but also reduce it. So auto sort of makes it either fully auto expects the goal to be proven, or it doesn't do anything else, right? But propositional, if you just have some complex propositional logic, sort of breaks it down into individual goals. So it's a useful tactic. We'll see some of that later as well. So I'm just introducing propositional here just to show that it's trivially true, but I'm just using propositional because I can make this go through with propositional as well. So similarly, this one also goes through. Okay, that's fine. So so now what we have is we proved the base case. Now we have to do the inductive case. So I'm going to invert H here. So what do I know about increment to invariant on S? That is so increment to invariant on S has a specific structure. right? So when I know that it holds on some S, I know that it holds on, I mean, this property holds and this property holds, which is what I have obtained from here. And S is itself a particular record that has this structure, right? That is what has ended up happening here. So yeah, I mean, it's just structurally pattern matching and then making facts obvious. We're going to keep inverting, right? So there are two steps for taking a step in a parallel transition system. By inverting this, I'm going to end up with two subcases, one for the first thread and one for the second thread, P step 1 and P step 2, right? And then there are many ways to actually take a step on a single thread, right? So here, all of the program counters, right? The PR1 and PR2 are sort of uh, undefined. It could be an arbitrary PR1 and PR2. So I'm going to, so the increment step H6 says that I am taking a step in the first thread from PR1 to PR1 prime. And there are several ways to do it, right? So if you sort of look at the definition here, there are 1, 2, 3, 4 ways to do it, right? So when I sort of invert this increment step, I'm going to build up goals for all of these. This is like essentially doing case analysis, right? So you're essentially doing, oh, there are 4 ways to do it. Let me go through all 4. Because this is an inductive, you can just invert it. And what a cock will do, this nice tactic will do, is make individual cases for all of the specific ones. So as I invert H6 and simplify, you will see a lot more goals. So let me make it like this. So I inverted. I have so I had 2 goals initially. This is going to produce 4 sub goals, and this goal is going to go away. So that's why I ended up with 5 of these, right? So 1 is gone, and then 4 sub goals. Now each one is going to show, right, individual case. So go from log to read, and then the second one will be read to write, and so on. So you have to essentially go through each of the cases. Yeah, so there is this is just the, so the meta point that we are doing here is the proof assistant is not simplifying any of the proof sorry, the proof assistant is not simplifying the intuitive reasoning that we are doing when we actually reason about exponential number of schedules, right? But it's just making everything obvious for us and adding rigor so that we can do the reasoning without making mistakes, right? That is what it is helping us. But here we are forced to go through each of these steps. Of course, you can automate it and make it better, but the human is in fact in the loop, and we have to deal with all these sort of different interleavings, and this is what we are doing, right? So again, the way to, we need to show that we have this instruction OK PR2 lock, right? And in order to sort of prove this, right, we are going to use this fact, false equals hash lock of PR2. We are going to destruct PR2 to find out, we are going to apply case analysis on PR2 to find out what are the concrete values of PR2 where this is false, so that we can use that as part of the further proof, right? So we are doing cases PR2 simplify, more goals, right? There are several possibilities for that, and all of these are sort of going to be explicit now. And now we sort of expanded. If you sort of look at this goal, right? So we have obvious things here, and now we have to show this holds. Essentially, what I have to do now is to show that increment 2 invariant holds on this state, which is fully contains only ground things, right? There is no complicated definitions. All I have is locked, global, and these private state. I need to show that this fact holds. So I'm going to apply inc to invariant prime, which is the definition that I have here, right? I need to show these properties actually hold, right? Which is what I will be asked to do. There is this shared from private definition, which I unfold and simplify. So let me do that. So more definition, but if we sort of look at this, at this point, it is similar to what we ended up with uh, in when we prove the base case, right? So this is an equality that goes through. Again, equality. Again, equality also makes this go through. So of course, right? So if you looked at the state here, it says false equals hash lock of PR2, and we just case analyzed the PR2. So it sort of had many cases, but hash lock only holds on certain cases, right? Um, Essentially, when you're just before executing a lock, hash lock holds, but when you're actually in the read instruction, when you're reading the global variable, hash lock is actually true. So we are going to end up with contradictions in the assumption, right? This is precisely what happens here. So because the first one is because PR2 was specialized to the case lock, and there it hash lock will evaluate to false. But here we are in the state read, right? We are in the state read. So we are holding the lock. So it cannot be the case that this invariant can hold, right? Two threads are in read. This is not true. But thankfully, we have um, a contradiction in the assumption, right? Essentially, we have the fact that we assumed that the lock is not held by the second thread because we assume that we are in the read state. But if you actually want to pick the read state to be for the second thread, then the hash lock is true. So we will end up with the contradiction. So equality also derives, equality derives contradiction from this one and make it go through. Equality is a bit powerful, right? You can also apply contradiction. That's fine. But if you apply equality, the contradiction makes it go through. Again, we are going to see contradiction for the other rules as well. So wherever we are in the critical section on the thread 2, we are going to see contradiction because the first thread is actually in the read state, right? It cannot be the case that the first thread is in read state and second thread is doing a write because both are in the critical section. And thankfully, the way we set it up, we can derive contradiction, right? And for the last one, where we are still in read and the other state is done, there is no contradiction. So we have to prove that this invariant holds on the state. So we apply increment to invariant, unfold short from private, simplify. I mean, the proof itself is simply goes through with equality, right? And we have done exactly the initial state for the increment system, which is lock. We've done read. We are now doing write, right? And we have to go through the same set of steps for doing this. Cases PR2, apply, uh, go through each of these in very detailed way, right? So again, we destruct PR2. We will end up, we are assuming that the PR2 is not in critical section. So a lot of these will introduce contradictions. So all of that is there. So essentially, you can go that in detail. I mean, the proof is just long. So at this point, we just done one thread, and you have to do the same for the other thread as well. So the point takeaway, I mean, you can go through it. You will sort of see that we are applying the same sort of principle, right, as we have just seen, right? But the point is, we are specifically sort of showing I am first thread is in the first instruction. We are iterating through all of the instructions, and we are proving that either that the state is incompatible according to our definition, or that the value is going to be the counter value is going to be what I say. That is what we are doing for each of these, right? There is a product of these. Uh, so that's the exponential number of states we end up with. Right? But the point is, we can easily automate it. I'm not going to. I mean, I can explain it very at a high level what happens. So whenever we saw increment to invariant, these inductive definitions, right? We were inverting the definition. So I'm pattern matching on the goal. Whenever we see any of these, we are applying invert on the tactic. So that's fine. That is what I ask Coq to do in this repeat, right? And whenever we see a PR increment program, I am actually doing case analysis. right? So I apply any of these, and this is the case analysis that I do here. Cases PR1, cases PR2. I'm sort of pattern matching on if there is a PR in the context, right? Do case analysis on PR. I mean, this is going to produce a large proof tree, but that is what I want, right? Initially, I do apply invariant induction and simplify, right? That is what I do here. I started there, right? So I applied invariant induction and simplify, and I kept applying inversions. I sort of then I did cases PR2, right? So that is what I've encoded here in all of this, But then after I've done all of that, in the cases that are left over, I try equality, right? I tried equality. Equality sort of derived contradiction from everywhere. In cases where we couldn't derive contradiction, I actually applied the zinc to invariant prime, unfold shared from private simplify, and then equality made it go through. So this is what I have defined here. So when you cannot prove it by contradiction, then you go ahead and apply the invariant definition on the state. And the rest of it, you just unfold and simplify. Equality will make it go through. So the whole proof that we have, which is very tedious there, can be sort of compressed to this one, right? So this is the power of automation. It's sort of it takes time, but now we are done. We've actually proved that this invariant that we define, this increment 2 invariant, is actually the invariant. It's actually an invariant for increment 2 system, right? So that is what we've done. So in order to prove our final result, right? The final result is just talking about the last state, which is done and done. So we want to sort of say that when we are in the final state, this is the property that we have. So we are going to use this general notion of invariant weakening, which is to say that if I have an invariant, which is say, we'll just walk through the definition itself, right? If I have a transition system sys, and I have two invariants, such that I know that invariant 1 is an invariant for the system, and whenever invariant 1 holds, it implies invariant 2. Then it means that invariant 2 is also an invariant for the system, right? So this is by sort of intuitive reasoning. I have a strong property which implies a weaker one. Then if the strong property holds, then it means that if the strong property is an invariant for the system, then the weaker property is also an invariant for the system, because it always holds, right? You can make the invariant as weak as possible. So you can have an invariant which is always true, right? This is not useful, but it's an invariant. So anything implies true. So this particular fact is true. But what we usually do is we prove a strong inductive invariant, and we want to prove something on the final state, right? So we are going to use this invariant weaken in order to sort of go from something we say on the final state, right, to strengthen it and then say we are actually going to use this increment 2 invariant, which is this inductive invariant that we just proved, right? And we will also be obligated to prove that whenever this invariant 1 holds, which we will sort of see, the final invariant that we want to show also holds, right? So again, the proof is very simple. I encourage you to go it in your own time. So what is the actual invariant that we want to prove, right? So let's expand this one so that we can see what we want to do. So the intuitive definition which we said, right, at the end of the program, the counter has to be 2, is captured by this, right? The private state of the system has to be done. This parallel system has to be done, right? If it is done, then what we are claiming is that the global state is 2, right? And what we want to prove is that when we take this increment 2 system, which is a system with 2 threads, we essentially we pick S to be all of the reachable states, right? So this is just saying S is one reachable state in the system, and what we are saying is that the reachable state has the right answer, we have a precondition here, right? The reachable state. You can reach the state in many ways. So you could have taken you could have executed the first thread fully and then executed the second thread fully, or you take one step at a time, right? Or you take two steps here, one step here. There are several different ways to reach the final state. We define the final state as done done, right? And we say that if you ever reach done done, then the global state is going to be 2, right? That is the property that we have defined here. This is the actual thing that we want to prove, right? We start with that system, we reach the state, and the reachable state has the right answer. The precondition is that in the reachable state, both the threads are done, and it has the right answer. So, so again, so observe that this is not an inductive property, right? So this is like this is sort of I mean, this is not a useful property that you can prove by induction. Although this says something about the final state, this property says something about the final state, you cannot use it to reason about the state at some intermediate state of the program, right? It only says something interesting about the global state when the state is done, right? So we couldn't have directly proved this fact as is. We have to have proved this inductive invariant and use it to prove it here, which is what we do here, right? So we sort of say, simplify this first, right? I want to show that increment to right answer S holds. And the way we show that is, recall we had this use invariant, right? In order to show that some invariant holds on S0, right? I need to show that S0 is reachable from that system and some invariant is an invariant for the system. I'm going to appeal to that. So I'm going to apply apply use invariant. So I want to say that this increment to invariant is an invariant for the system. This will be filled in, right? And this S, which is the final state that I have here, is also a reachable from the system. And because I can't prove that directly, I'm going to use increment to invariant that I just proved is an invariant for the system using this invariant weaken. So essentially, intuitively, what is happening is that I'm going to prove the stronger property, which I have already proved, but I'm going to use the stronger property, right? And I will show that this property will imply the invariant, the weaker invariant that I want to show, which is the invariant that is here, right? And this apply invariant with weaken where invariant 1 colon equals increment 2 invariant. This is this with clause is used to specify a specific value for a quantified variable. So if you sort of look at what invariant weaken is, right? So it says invariant weaken has these variables, right? What is invariant 1 and what is invariant 2? I can specifically give assignments for these variables by using this syntax. It's just syntax. There's nothing interesting happening here otherwise. So if you say I'm going to apply invariant weaken, I have some preconditions as well, right? So that will come up here. So I'm going to apply invariant weaken, so I have to prove these preconditions. Let's see what they are. So I'm using increment to invariant as the stronger one with which I'm going to prove this. So I have to show that increment to invariant is an invariant for the system. This is fine, right? This is what we just proved here. Invariant, increment to invariant okay, which is what we proved. So I'm going to directly appeal to that. So that's done. And the second one I have to prove is that the stronger invariant actually implies the weaker one, right? So this is quite straightforward. You don't have to do much here. So I do a bunch of inversions. Increment to right answer is the definition. So I unfold it and simplify. And I invert head 0 just to show that do the substitutions for the obvious facts, right? Wherever PR1 and PR2 are, substitute them with done done. So you will see that all of that is done here. And then we have contribution from done equals 2. You do simplification, you have 2 equals 2, and that's done. And S is a reachable system. That's an obvious fact that is in the assumption. So that one also goes through. So what we've done is that we proved that the final state has counter 2, and the way we've done it is we proved a stronger inductive invariant, and we used that invariant in order to prove the weaker goal that we actually wanted to show. So this is going to be a recurring trend. Okay, so this is what we are going to see. And I'll stop here. I know I've taken a lot of time, but I want to finish this so that I can release the assignment. And we will we'll meet anyway tomorrow, so you can ask questions tomorrow if you have any questions on this one. I recommend you to go through this, right? So because this will be quite handy for doing the exercise, and we have to go through each of these steps as well. Anyway, I'll stop here, and then we can I'll take questions tomorrow. Thank you.